Thank you very much. So thank you very much for giving me the opportunity to give a bit of an ad hoc introduction to some of the things we've been doing recently. So in the sample preparation discussion yesterday, we spoke a lot about the air-water interface, and I alluded to some work that we've been doing to make grids very quickly. So I should say that this is a presentation which I've basically taken a presentation that normally takes me 40 minutes, deleted a load of slides, and now I'm going to try and rush through the slides I've got in about 5 minutes. So if I'm going too fast and you don't understand what I'm saying, please just stop me and ask questions at any point. I think it'll work better if it's more of an interactive session. So basically, we became interested in this because Steve Munch at the University of Leeds has a number of biological systems where he wants to perform time-resolved electron microscopy. So he was interested in systems where he could take, for example, an enzyme and a substrate, or a macromolecular complex and ATP, and then rapidly mix those together and freeze them on a defined time period. The device which they've created is in collaboration with Howard White, who makes a lot of these devices. So Howard's the real, I guess, engineering brains behind this device, and he makes lots of them, which are in labs all over the world. So Joachim Frank's time-resolved device was made by Howard, for example. So this is basically an overview of the setup. Nobody has any plans to commercialise any aspects of this, so all of the plans are completely open and available. Howard is very happy to talk to anybody who wants to either pay him to build one or build one themselves. But basically, she says with the laser, is this the right one? Yeah. So basically, we use a Vitrobot styrofoam bucket. You have a spray nozzle here, and we just use gas pressure to generate the spray. And then your grid is held in the tweezers here, and then on the next slide you'll see this is it in action. So, and this is real time. So the spray is initiated, your protein solution sprays out of here, droplets land on the grid, and then it lands in the liquid ethane. And in slow motion, we can see how wobbly that is on this 16. Yeah, that's playing now. You can see the grid coming down and freezing there. So this device is incredibly flexible, so we can adjust the speed by changing the position of the nozzle, so making and also changing the speed of the plunging arm. That means that we can we adjust the speed just by adjusting nitrogen pressure, which means that we can move that arm basically as fast or slow as we like. So the fastest that we've made grids that we've actually imaged at the moment is 5 milliseconds, but from a hardware perspective, there's no reason why we can't go much faster. So the spray, as it comes out of the nozzle, is initially a jet and then turns into these droplets, which are about 20 to 25 microns in diameter. They then land on the grid, which is vitrified. So Chameleon and Vitrojet and all of these systems are things which people, and cryoERIC are all systems which people are coming up with to make reproducible, beautiful grids. Quite clearly, our system is not a system which is going to be making reproducible, beautiful grids. The grids are awful because you have these. So basically, the droplets land on the grid, and then we have to find these thin regions at the edge of the droplets, which we can then image in. So if we make grids at 50 milliseconds, the droplet tends to have had enough time to spread out, and you do get a fair amount of usable area. You can easily set up overnight collections. If you make the grids at 5 milliseconds, you tend to find that these thin regions at the edge of the droplet are even more rare, and the ice is much, much thicker than we would like. So if we freeze grids at 5 milliseconds, for example, the ice is often an average of, say, 80 nanometers thick or something like that in the regions that we use. So this is not a way to make beautiful, lovely grids. But my interest came into this and saying, in terms of saying, okay, well, we can make grids really, really quickly. Wouldn't that be interesting just to see and look about how macromolecular complexes behave on those very fast time points, and to see if we can learn something generic about what particles are doing on the low millisecond time point. And of course, we were also, this part of this work was of course inspired by the lovely eLife paper that came out of NYSBC, Alex Noble doing tomography on loads of things. Hello.
Do you have a way to control the spray in order to reduce the size of the droplets?
Yes, you can reduce the size of the droplets a little bit, and we have done that, but we tend to, that droplet size that seems to be the one that gives us the most usable area. But I think that what we probably need to focus on is changing the grids so that the droplets actually are actually spread out. Yeah. So so what we were first interested in doing is looking at the air-water interface. So Alex Noble's work mostly, used lots of different kinds of grids, but the spot-atom grids that were made, I think it was about 200 milliseconds, something like that. Yeah, just for information. So, we chose to basically look at 3 specimens in the first phase of the work. HSP60 has got, if anyone who's worked with it, has got a very, very strong preferred orientation, so that's why we picked that one. And basically, if we make grids at and on the Vitrobot, we can see basically all of the particles are up at the air-water interface. If you make them at 50 milliseconds, you have them. It depends on the area, but they're basically still all up at the air-water interface. If you make them at 6 milliseconds, then you are starting to see a bit more of a spread, but quite often they're all still up at the air-water interface. So this is a statistically significant difference, but I would argue that even at 6 milliseconds, the chances are, if you look at any given particle, it's going to be up at the air-water interface. And this, so this is quite a neat linear this is quite a neat correlation with speed, but the data doesn't always look that nice. So with apoferritin, the data is a little bit more spread and a little bit more messy, and we can speculate as to why that would be. But again, significant number of your particles all up at the air-water interface. I actually think the reason that we end up seeing these populations here is because you will quite often have a situation where the grid is quite crowded, so the air-water interface actually becomes saturated, and I think that would then mean you're more likely to have particles in bulk. If we look at making grids at 200 milliseconds with the chameleon, then again we see all of the particles up at the air-water interface. So this was the test that we did with ribosomes. So that shouldn't be a surprise to anybody, because if we look at this paper from Chris Russo's lab, if you do the theoretical calculations for our proteins of interest, the particles are going to be interacting tens of times within a millisecond against the air-water interface. So even if we're making grids at 5 milliseconds, we're not able to outrun those air-water interface interactions. So there is a small shift the faster you go with particles going into bulk, but what are the particles? They might be at the air-water interface, but are they doing something different at 5 milliseconds versus if they've been sitting there for a second, for example? So the first thing we decided to look at again was HSP60, and if you just take a normal blotted grid and do a normal standard non-tilted collection, you can't do a reconstruction because the preferred orientation is so strong. So we just did a 20-degree tilted collection. We collected quite a big data set, and it's horrible. And then we took one of our 50 millisecond sprayed grids and did a reconstruction of that, and it was a much smaller data set, and the reconstruction looked a bit better. So we were like, oh, well, the particles are at the air-water interface, but maybe they have a slightly bigger distribution in angles. Let's look at that in a little bit more detail. So if we have a look at if we have a look at the angular distribution, so these are angular distribution plots. Where you see these blue colours, this is essentially a peak or a hot spot, as I call them, and then for example down here where you've got much more of a blur, that's showing you that you have more of a wide range of angular distribution. So you can see that on the Vitrobot we have very strong preferred orientation. If we go 50 milliseconds, few more views, 6 milliseconds, more views again. So for this particular protein, the faster you go, the better our angular distribution, and that helps us to generate better quality 3D reconstructions. Pictures, not always that simple, however. So the next thing we tried this on was 70S ribosomes, and that was lovely because they weren't all 70S ribosomes. We also had 50S and 30S in there, which gave us a really nice way in to start looking at what different but related particles will be doing on different time points. So if we take the 30S, then this basically corresponds to what we saw with the HSP60. So if we look at these angular distribution plots, it starts, the faster that you go, and the more, the better your angular distribution. If you really have a look at this one's really interesting because as you kind of get slower in terms of, as you go from these fast grids to these slower grids, the range of views actually remains about the same, but the hotspots are changing. So basically what that's telling you is that the protein is going up at the air-water interface, it's exploring its local energy landscape, and then is kind of at some point deciding to kind of flick to a particular orientation. And we wanted to speculate as to why that would be. So for these ribosomes, we were able to see that a particular density corresponding to a particular protein, in this case L31. If we look at 13 milliseconds, it's there very strongly. At 50 milliseconds, 200 milliseconds in this one, it is still there, but it's faded. And then if we have a look at the blotted grids, it's completely gone. So it might be that when we see examples like this, that we're having either a small amount of protein unfolding and that's changing the way in which the protein is behaving at the air-water interface. So fast grids, you have a small difference in partitioning. You have a small but sometimes significant and useful difference in angular distribution. But the thing that I want to highlight is the big difference in concentration. So I'm probably out of time. So I'm just going to leave this one up here because I think this is really weird and interesting data that I would really, really like people's views on. But basically, this red line is the amount of protein that we applied to grids. We can see in blotted grids, you see huge concentrations compared to what was applied. And we can see that if you look at 50 milliseconds, then you have about what you would expect. But consistently for HSP60 and apoferritin, you see almost no particles at these time points. And we have some theories as to why that might be. Basically we can't explain this data because it's a bit weird. So I'd be very happy to talk to that with anybody in more detail if they want. Right, I'm done. I've got more slides.
Thank you very much, Rebecca, for very precise and very fast talk. You cannot leave it without discussion, so whatever. Please, start.
So you said that you had 5 milliseconds time.
Yeah.
Does this include the time that the droplet needs from the nozzle to the grid?
Yeah, that's exactly, and that's 0.5 milliseconds.
Because also in the droplet it has an air-water interface.
Absolutely, absolutely. So one of the things we quite like to do is build a chamber around it, flush it with something like chloroform and just see if that makes a difference. I haven't got that one past health and safety yet.
Do you see a protein scale build up on your nozzle?
We have not looked for it on our nozzle. We know, so we changed nozzle types. So on old nozzle types, we gold labelled some protein, and then we saw when we sprayed that all of the pipes and the nozzle were turning a funny shade of pink. So we were assuming that the protein was then associating and sticking. But we've recently changed nozzle types, and we don't see that behaviour anymore. So.
Gabor?
I've seen that you spray perpendicular to the grid traveling time. Did you try different manuals to smear it more out?
Yeah, it's an interesting idea. So the behaviour, so we call it the spray cone. So you end up with this spray cone, and although the droplets start off at that kind of angle, they actually you end up with a natural dispersion of droplets anyway in terms of their angle in which they hit the grid. And that's one of the things that really worries me about this system, because we don't understand the shear forces that the proteins are being exposed to as the droplet hits the grid. And I'm sure that those forces are going to be affecting the ways in which the protein behaves, but it probably explains some of the heterogeneity we see on these grids.
So the last question. Bruno. Sorry.
I was wondering also about the droplets. The formation of these will depend on the air present also, no? Because that's hitting and shaping, as you could see in the film.
Yeah.
So what about reducing the air pressure in the chamber so that this would be, giving maybe finer droplets or behaving differently?
Yeah, so that's an interesting idea. So we've been working primarily with Martin Trevin's group, who have been working with the XFEL beamlines to look at spraying microcrystals. So that's their primary interest, and we've just kind of hijacked onto that technology. And there's a huge amount that you can do in terms of that nozzle technology to change the way in which the droplets are dispersed. I think our primary problem is the time, because the droplet, in terms of the time, in order for us to get the time resolution we want, the droplet hits the grid, and we need to encourage it to spread out so that we have as much thin usable area as possible. And I think that both. Yeah, so we tried smaller droplets, and we tended to end up with not enough droplets on the grid, because I think I think we might need to go back and have a look at that. Yeah. Sure.
You say if at the shorter time you see more particle in the grid, or you need more higher concentration for making grid.
So this is a fold change. This is a fold change. So we see that when we make grids very quickly, there are almost no particles, and this is almost none. This is really, really striking for some specimens, and then for ribosomes, it is what we would expect compared to what we applied. Yeah, so I think that this could be evidence that you have a phase. This could be potentially quite controversial. I think that this could be evidence that there is a phase when you make grids where you get a rapid denaturation at your initial exposed clean air-water interface. So essentially, the proteins that are in that, as the droplet spreads out, the particles that happen to be there are interacting with a clean air-water interface, and for some proteins, apoferritin and HSP60, they're immediately unfolding, and you're ending up then with a layer of denatured protein on the grids, and then. In our system, we then have a thick droplet off to one side, and then the particles are then able to diffuse from that thick droplet back into the thin film, which is why we then see a repopulation after 50 milliseconds, and then this gets stronger again after 200 milliseconds on our sprayed grids. Yeah.
They still need the spread time also.
Yeah.
Yeah, because I saw you say the shorter time you reduce the air interface, the concentration, like the less particle will accumulate in the air interface.
Yes, slightly.
You also need lower concentration. You don't need a higher concentration. What I try to understand. So if you need a very high concentration, but this is the blotting experience. If you have a lot of particles go to the air interface, water interface, you need a higher concentration to get the higher concentration to get enough particle you can look at. This is by blotting method. So this was I try to understand what your one. But your one is you need a time to get more particle into the view and into the grid.
But you would imagine that the particles in the droplet are monodispersed within that droplet, aside from some air-water interface.
So maybe every stop you've got a layer of air-water interface.
Well, in fact, we have good evidence for that for some protein specimens because...
It must interfere.
Yeah.
It's a great discussion. It's growing. I feel it's growing.
Yeah.
We should now do opposite thing because we have to move to the next session. Please.
Yeah. Thank you. I'm just...
Please, you started. We
no, it's fine. No, it's fine. So
Tell something.
So I think that for some protein specimens, we probably do get these... we do see evidence for protein rafts. So the reason we see that is we get in some tomograms extremely asymmetric distributions. So you'll see one air-water interface with loads and loads of particles, like in here it's completely coated, and then the other one far, far fewer. Yeah. And you can imagine that's because in the droplets, particles are forming these rafts at the air-water interface. Those rafts are just marauding across the grid, and sometimes they're in the thin areas so that you can image them, for example. Yeah. But I really, really, really need a way of being able to directly prove the presence of a layer of completely denatured protein. So if anybody has...
label it.
What was that?
Fluorescently label it.
Yeah, we tried that, but it's very difficult to normalise it for ice thickness. Yeah. We tried that. I'm wondering if you could do something clever with eels, for example, over bare ice versus ice with denatured protein. Anyway, if anyone has ideas, I'd love to talk to you afterwards or email me. Thank you.
I feel very bad as I'm cutting a live tree,
No,
but
it's
we
fine.
have to stop.
No, this was a bonus. This was an added whatever. Thank you.
So we have to move to the next session.